Let's talk a little bit about the role of the solvent in the SN2 reaction. Once again, here's the rate law for the SN2 reaction. Notice that the nucleophile does make an appearance in this rate law, and so the rate can be affected by changes to the nucleophile. Here's what the transition state looks like for the SN2 reaction, where you have bond formation occurring at the same time as bond breaking. So let's think about what would happen if a nucleophile were heavily solvated as shown here. We remember that the transition state for the SN2 reaction is already crowded, and the more steric repulsion that is present, the higher the activation energy will be for the rate determining step. So a heavily solvated nucleophile is just going to increase the sterics in the transition state by carrying all of these solvent molecules with it. Therefore, SN2 reactions work best when the nucleophile is not solvated. This is where the polar aprotic solvents are going to come into play. And as the name implies, polar aprotic solvents do have a dipole, but they cannot donate hydrogen bonds. So they're not particularly good at solvating anions. So something like a nucleophile that's either negatively charged or very electron rich will not be solvated very well by these solvents. I'm going to give you a couple of examples over the next few slides of some very common aprotic solvents that we will encounter. Acetone, shown here, is going to be used a lot, as will DMF. The full name is N,N-dimethylformamide, but you're going to see DMF used most commonly. A couple of others here, we have dimethyl sulfoxide, otherwise known as DMSO. Ethyl acetate is very commonly used. Tetrahydrofuran, or THF, is a very common solvent, as is acetonitrile. So all of these are going to be examples of polar aprotic solvents that you may see starting to appear in the reactions.